Welcome back to my lectures on Galois theory. We're going to start another topic. It's called algebraic extensions. Algebraic extensions. We need some results from some definitions and results from vector space, linear algebra. So what I'm going to do is to get in touch base with some of the definitions and results which we require for the algebraic extensions. So let us start with the definition of a vector space. I'm not going in very detail into vector space because that is not the focus here, but I still want to use some results. So definition, let F be a field then a vector space V over F, or you can also say as F vector space. Is an abelian group with a left scalar multiplication of each element from F with each element from V, with or having the following properties. So V is an abelian group, a non-empty abelian group, and F is a field. So the first property is, what it says is we can multiply an element of F with an element of V. So there is actually a map from F cross V to V. That is called the multiplication. So with this property, the property is like this. For every A, B in F and alpha, beta in V. By the way, the objects, the elements of V are called vectors, and the elements from F are called scalars. For every A and B in F and alpha and beta in V, we have A alpha, A times alpha, this is a left multiplication, always belongs to V. Second property is A plus B of alpha. A plus B is possible, A and B are from a field, so addition is possible. Times the scalar multiplication equals A alpha plus B alpha. Third one is A times alpha plus beta is equal to A alpha plus A beta A plus B is defined properly because A and B are from an abelian group. So the scalar multiplication of A with the sum of two vectors in V is this. And the fourth one is A times B alpha is equal to AB times alpha. See, this is a vector in alpha in V. So you are multiplying that vector with another scalar. That will become the multiplication of scalar, which is defined properly because A and B are from field, times alpha. And 5, 1 times alpha is equal to alpha. 1 is the multiplicative identity in F. That times alpha is always. So these are the properties of the scalar multiplication. Some examples are, I'll give you one example. R cross R over R. So what it means is, see, if you take A, so 2 times, this is probably 3, 1. I'm going to define as 6, 2, which is also in R cross R. So you can verify all these properties when you consider R cross as a vector space over R. Another vector space is if you take the polynomials of over a field F, then this is a vector space over F. Because if you take an element, let's say 3x squared plus 4x plus 1, that belongs to F, this times another vector says 6, this actually belongs to F. So if you multiply this will be 18x squared plus 6x plus 1. And that belongs to F of x. And similarly, you can verify each one of these properties and you find that this is also a vector space over F. Let V be a F vector space. We'll continue with some more definitions. B a vector space means it's a vector space over F. And let S is a subset of V. A non-empty subset of V. B non-empty. Then we say that the elements of S are linearly independent if A1 alpha 1 plus A2 alpha 2 plus dash 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 plus AN alpha n is equal to 0 implies ai's are zeros. If this condition is satisfied for all alpha 1 dash dash alpha n belongs to S. For any combination of these alphas, if this condition is true, then S is linearly independent, or the elements of S are linearly independent. For example, if you take this R cross R, okay, then I'm going to take just one element. Let's say S is equal to 3, 2. That belongs to definitely R cross R. So it's a subset of this. So this is a linearly independent set because there's only one element here and there is no alpha 1, alpha 2 and all, just one element alpha 1, that is this, and you are adding and subtracting. There is nothing to add and subtract here, there's only one element. So if you want this to become 0, then you have to multiply 0 times this. So A1 is 0. We'll take another example here. 0, 1 and probably 3, 0. It's actually R cross R. This is also actually here it is going to be 0, 0 because it has to be an element, additive element of R cross R. So this is also a linearly independent because 0, 1, this is our alpha 1, alpha 2 is 3, 0, and if you say you are multiplying this, A2 is equal to 0 means 0, 0, that means this is actually going to be, what is this? This is actually A1 times 0, so this is actually 0 A1 plus this is actually 3 A2 comma 0, and that is actually equal to 3 A2 comma A1, and that is equal to 0 only if A2 equal to 0 and A1 equal to 0. And that actually satisfies this condition. So this is also a linearly independent collection of vectors from R cross R. I'll take one more example just to show that there is something called not linearly independent. For example, if you take, let's say take S1 as 2, S3 I am taking it as 0, 3, comma, or 1, 3, comma, 3, 9. This is a subset of R cross R. This is not linearly independent because if you can do 3, so if you take this one as minus 3 times, minus 3 belongs to R. So this actually becomes 1 times. So this is our A1, this is our A2, this is our alpha 1, this is our alpha 2. So multiply 3 minus 9 plus 3, 9 is equal to 0, 0. See, these vectors are not linearly independent because we can find non-zero scalars such that when you do a multiplication and add together, you can get still zeros. Without the A1 and A2s are not zeros. So this is a linearly dependent collection. These two are linearly independent collections. So that's what I meant here. definition is, let V be an F vector space and S is a subset of V, be a non-empty subset of V, then if for every alpha in V there exists alpha 1, alpha 2 dash dash alpha n in S such that alpha is equal to a1 alpha 1 plus dash dash an alpha n for some ai's in F. That means you can find, for every element you can find a linear combination of alphas from S and scalar multiplication from F. You know, if you can do you can find a linear combination. In every element there's a linear combination of this. Then we say that V is spanned by S. For example, here R cross R over R, if you take 0, 4 and 1, 0, and if you take any element from here, for example, let's take 1, 1, and this is our S. So 1, 1 can be written as this is our alpha 1 and this is our alpha 2. Alpha 1 plus, actually 1 time alpha 1 plus half of, 1 time alpha 2. 1 time alpha 2 plus half of alpha 1. See, 1 time alpha 1, alpha 2 is actually what? 1, 0 plus half of this. So, oh, sorry, not half, it is actually 1/4. So this will be 0, 1. And that is going to be 1. So you can find 1, 1 as a linear combination of these two elements. So these two elements actually spans F. Spans V. We can keep on adding stuff like this here. Again, 4, 3. So you can keep on adding this till it spans R cross R. Now we are coming to the another definition. Let S, I'm assuming that V is a vector space, be a subset of a F vector space V spans F, spans V. That means this actually spans V, meaning every element of V can be expressed as a linear combination of scalar multiples of elements from S. Let this and S be a linearly independent set. Then S is a basis for V. S is a basis for V. For example, here 0, 4 and 1, 0, this is 0, 4 and 1, 0, this is a, I will explain that in a different way. Okay, so that is it. So what I'm saying here is, if you take R cross R over F, then the set that contains 0, 4 and 1, 0 is a basis. This can span every element of R cross R. But S equal to 0, 4, 1, 0, 4, 3 is not a basis. Because this is not linearly independent. You can find A1s and A1s, A2s, ANs such that this combination is true. So this is a linearly dependent subset even though it spans V. But this is a linearly independent set that spans V. So this is a basis and this is not. We have a couple more results and one definition. Let V be a F vector space. Then and S be a finite basis for V. For example, here R cross R, the base we found is like something like 0, 4, 1, 3 or 0, 4, 1, 0. This spans R cross R. So to find out every element of R, we need only these two elements to express any element in R cross R. So this is a finite dimensional vector space. So it's called, if S be a finite basis, then V is called a finite dimensional vector space. Finite dimensional vector space. Otherwise, it is infinite dimensional. And we normally use dim of V to denote the dimension of V. Now there are two results. Result 1. Let V be a vector space and S be a subset of we'll say this Let B be a finite dimensional vector space. Well, let B be a finite dimensional vector space, and S is a subset of V with the cardinality of S, that is number of elements in S, is strictly less than the dimension of V. Then S cannot span V, or S cannot be a basis for V. Result 2, let V be a finite dimensional vector space, and S is a subset of V, and the cardinality of S is greater than the dimension of V. Then S is linearly dependent. That means if you are adding one more element here, then it will become linearly dependent. You cannot make it as linearly independent set. So with these definitions and results from vector space, let's come back to our topic, algebraic extensions. So we are going to realize or identify the simple extension as a vector space. So let E be an extension of F, and alpha belongs to E, be algebraic over F. Algebraic over F of degree n. That is actually degree of alpha over F is equal to n. So what can you say about the simple extension for alpha over F? This is actually equal to A1 or A0 plus A1 plus A1 alpha plus dash dash A n minus 1 alpha to the power of n minus 1 AI in F. So F alpha contains polynomials in alpha with degree less than the degree of the irreducible polynomial of alpha over F. Give an example here, the normal Q root 2 example, or Q root 2 is here, and this is my Q root 2, the simple extension of root 2. And here what's the elements of this field, this extension field, are A plus B root 2 such that A comma B in Q. Something like 1 plus root 2, 4 plus 3 root 2. These are all elements here. And also we can have 2, 3, 4 or half, because these are all comes under here. These elements are outside Q, and the elements that contains root 2 are here outside Q, and the elements that does not contain root 2 are here. So that is what this one is. So we are actually spanning f of alpha with elements like 1 comma alpha square plus dash dash alpha and minus 1. Because any element of f alpha can be written as a linear combination of these elements with coefficients from f. That is exactly what we described as a vector space. So we can consider this as, we can consider f alpha as a vector space of dimension n, because there are n elements here, 1 alpha dash 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 alpha to the power of n minus 1 over f. Okay, so this is the reason why we defined the vector space before we came to algebraic extensions. Now let us take an element in f alpha. Let beta belongs to f alpha. What can you say about beta? Can it be transcendental, or it has to be always algebraic? Okay, so this is an element of f alpha. That implies 1 comma beta square plus comma beta to the power of n is a linearly dependent subset of f alpha. Why? Because the last result we saw that if the dimension is n, any element, any subset containing more than the dimension of the vector space are always linearly dependent. This has got n plus 1 element. So that implies there exists b0, b1 dash dash bn in f such that bi is not equal to 0 for some i's, because not all of them are zeros, such that b0 plus b1 beta plus b2 beta square plus dash dash bn beta to the power of n is equal to 0. That is a definition of linearly dependent. So what does this mean? This means that beta is a 0 of the polynomial b0 plus b1x plus dash dash bnxn. And what does that mean? That means beta is algebraic. So if alpha is an algebraic element, then every element in the simple extension of alpha are also algebraic. So if you take any element here, for example, here I'll show you what I'm talking about. See here, 1 plus root 2. Here, 1 plus root 2 belongs to Q of root 2. Our claim is this is algebraic because this is an element from here, just like beta. See here, if you take alpha is equal to 1 plus root 2, alpha minus 1 square is equal to 2, alpha minus 1 square minus 2 is equal to 0. So 1 plus root 2 is a 0 of x minus 1 whole square minus 2. So 1 plus root 2 is algebraic over Q of root 2. That is exactly what I am saying here. Now we are ready to define an algebraic extension. So let E be an extension of F, then E is algebraic. Then E is an extension, is an algebraic extension of F if every element of E is algebraic. Over F. Example, let E be an extension of F. We don't want to say this is an algebraic extension, any extension. Then alpha belongs to E, be algebraic. Then the simple extension F alpha is an algebraic extension of F. Why? Because for every element of this extension is an algebraic over F. That's we found in the last session. Now consider an extension E of F as a vector space E over F. Then I'm not going to say is algebraic or not, but we are going to see that it has to be an algebraic extension, because otherwise it won't be a vector space. Okay, we cannot express it as a linear combination. So I'm not going to say right now. I'm going to say that it's an extension. E is an extension of F, and consider E as a vector space over F. Then if E is finite dimensional, then the dimension of E is called the degree of E over F and is denoted by EF. This is a different way of expressing the dimension of the vector space. No, it's not everywhere, but in the case of field extensions, this is the degree of this. You don't call it as dimension, but it's called degree of E over F. Okay. When we define the degree, we didn't say anything about what kind of extension is this, if it's an algebraic or not. But let us assume a finite extension. Suppose EB a finite extension of F of degree n, that is equal to n. Now let us assume that, take any element from E, let alpha belongs to E. This implies 1 comma alpha square comma dash dash alpha to the power n are linearly independent, because there are n plus 1 elements here. The dimension is only n, so it has to be linearly dependent. Linearly dependent. These are linearly dependent. That means there exist AIs in F such that A0 plus A1 alpha plus A2 alpha square plus dash dash AN alpha to the power of n is equal to 0. And that implies alpha is a 0 of P of x equals A0 plus A1x plus dash dash ANx to the power of n. And what does that mean? That means alpha is algebraic over F. So if E is a finite extension, it has to be algebraic, because every element of E is algebraic over F. Now let us take two different extensions. Let E is an extension of F and K is an extension of E, where E and K are finite extensions. That is, E over F is equal to n and K over E is equal to m for some n and m in integers. So there are two bases here. Let 1 comma alpha 1 comma alpha to alpha n be the basis for E over F and 1 comma beta 1 comma beta 2 comma dash dash beta m be the basis for K over E. K E F. Now let us take an element from K. Let gamma belongs to K. This implies gamma is equal to, gamma is in K, that means it can be expressed as elements from here. So that means it is equal to sigma 1 I equal to 1 to m let's take up AI beta I. Any element of K can be expressed as a linear combination of this. For AI in E. Right? That is a definition of a basis. It can span the whole K with the coefficients from E. For each AI, we can again expressed as a linear combination of this. So this is actually equal to sigma I is equal to 1 to m. Each I to m, each AI can be written as j to n Cij alpha I beta j. When I say Cij means for each I there is a j. So this is where Cij belongs to F. What does that mean? This means that every element of K is spanned by elements of the form alpha I beta j. For alpha I belongs to E and beta j belongs to K. So we can think about this as a, see these, how many elements are there? There are m times n elements. So these m times n elements can definitely span K. But we are not sure this is a basis. To show that this is a basis, we need to show that this is linearly independent. So that is the next step. Let Aij or Cij, let Cij belongs to F such that sigma ij Cij alpha I beta j is equal to 0. If this is equal to 0, we need to prove that this is all zeros. See what happens here. See if you take this, you split this one into 2. I from 1 to m, and this is from 1 to n. Cij alpha I and beta j. This actually, if you take this part is actually 0 because this part is 0 because these elements are coming from this basis, and these are linearly independent. So this is actually sigma j is equal to 1 to n Cij alpha I is equal to 0 for all j. Sorry, for all I. But again, this is another set of linearly independent. This is also coming from another set of linearly independent set, that is in E over F. So this means that Cij is equal to 0. This is because Bj's are linearly independent. This is because alpha i's are linearly independent. So we have a set of mn elements that are linearly independent that can span K. So what is the result? The result is if K and F E are finite extensions of E and F, that is K, the degree of K over E is equal to n, and degree of E over F is equal to n, then K over F. See, every element of K is spanned by this combination where the Cij's are from F. So this is actually, we can consider K as a vector space over F. Then K over the degree of K over F is equal to Mn. Mn elements can span K with the coefficients from F. What does that imply? That implies that F is equal to K over E times E over F. And that is, see, this is E over F is n and K over F is n. And that's what is for.